in the UV as a function not of time, but of temperature. And the question one could ask is, what is the melting temperature of this protein? So once again, we can look at it in 2 dimensions, in 3 dimensions, and it's got wiggles in it and so on. But to tell what exactly is happening, and also in that context, we can take one of these curves, this one, and in principle it can be fitted, but why not take them at all the temperatures or all the wavelengths? Good. Just like we did the other one. Well, let's do our SVD. Aha, magic. Something happening as a function of temperature, a shape. A shape is a function of temperature, or a wavelength, controlled by temperature. 2 players, unequivocal. The remaining eigenvectors are flat. So we can say unequivocally there are 2 spectral components. Now, the program recognized that this was not kinetic, but temperature. So it allowed us to come up with the global, we call it equilibrium curves, rather than kinetic versus time stuff. So that's good. So let's go with 2. And then I'm going to say it's native protein. We heated it up as we might boil an egg, or and it went to an unfolded state, became unhappy. So if we do that, now these will likely ask us for our starting values, and I'll just guess it's something like 50,000, and the transition temperature I'll say is something like 60 degrees. Boom, good. So very quickly then, it says this blue stuff, very nice CD spectrum, as the temperature rose, got above 70, that collapsed. And some other form, this one, misshapen, not the alpha helix nice stuff, it appeared. And here's the residuals, and here's the enthalpy and so on. A very nice fit, an affirmation that we had a 2-species phenomenon, and the denatured protein has a different CD spectrum than a native protein. All the difference here being the mathematics used behind the screen and the z-axis or x-axis, whatever we call it, temperature and not time. Good.